Started. Everyone, welcome to the Friday IPS seminar. I'm excited to have our speaker for Mechanical and Aerospace Engineering, Professor Solmaz, who has the following background. Keep it brief, but I want to give our students some information about your prior research. So many prestigious awards, including the UC Presidential Postdoctoral Fellowship, the NSF Career Award, which was, I guess, a little bit early in your career. Publishing and senior member of IEEE various journals, primarily in control and network systems, which I have reviewed for a couple times. So, and we'll hear about her research on, we'll hear about specific research here, but her research broadly is about distributed optimization, coordination, estimation, algorithm design, and probabilistic multi-agent robotics, navigation, and motion planning. I will say that I teach our optimization courses in civil engineering, both in the undergrad and graduate level. So very interested to see what you're talking about today.
Thank you. We have to talk about that. Thank you so much for the nice introduction, and thank you for this opportunity to visit and share a little bit about my research. So I just wanted to acknowledge the contribution of my students, the current student Doni Tenure and Navid Rezazadeh and Yitan Chang. They are my former students graduated. So part of the research parts that come from my lab in this talk are just contributing with these studies. So before I start, because I'm a faculty next door, I just wanted to give you a little bit overview of what I do in my lab. My lab is called Cooperative Systems Lab in MA department. And my research interest probably is in the area of distributed algorithm design for network systems, and the focus is on optimization, estimation, and coordination problems. This organizes, I guess, in two research trusts in my lab. One is the multi-agent or multi-robot planning and navigation, which we cover various problems like localization in GPS denied output spaces. So I put some videos. Let's see if they play. Just to show you, we do hardcore research in robotics. We sense and build, and this is the LiDAR scan of this engineering gateway. So we do all of these things on the robotic side, like the exploration, all sorts of things. And then and the other trust is the optimization theory, which is like more theoretical, looking for alternative fast solutions for distributed optimization and large-scale combinatorial optimization problems. This is my current PhD students and one master students. So for today, I chose among different things that I could talk, coverage problem. And the reason I chose it was like, I think essentially coverage problem is operational research, and maybe I'm not going to talk about transportation problems specifically, but you can imagine many of your problems can be fit in this coverage domain. And also the other reason is that it's a combination of robotics and optimization. And I guess it's going to give me also an opportunity to talk about something that I'm not recently, but like the past 5-6 years, I'm very passionate about is the submodular maximization theory. And so let's get started. Let's see. So what is multi-agent coverage problem? So imagine we have a mobile agent. It could be a robot, it could be a drone, it could be an autonomous boat that you deploy, and you want to monitor a wildfire or fight fire, or you can, your interest might be cleaning an oil spill or providing extended wireless coverage, or in static setting, you can think about deploying traffic sensors in an environment, or you can think about deploying EV charging stations across a city. So all these problems are examples of coverage problem where we have to decide strategically where to place our assets to make the best of the tools that we have. So this strategic placement of agents across a geographical area, it has been with us like with human history. If you look at it, I think we always have this interest. But if we look at the literature, the rigorous treatment of this problem probably can be traced back to these packing problems, that they ask this question that if we have an infinite space and identical object, what is the densest way of populating that area? So in two-dimensional, we have the circle packing that goes back to 18th century. And then in 3D, we have this Kepler's conjecture that is proposed in 1611 and asks about packing the space with 3D spheres. So interestingly, the rigorous and the conjecture was proposed, a solution discussed, and then it is proven in 1998. So challenging problem, but anyway, these solutions are out there. And they're not necessarily a piece of history or historical value. Actually, people use them in their work. This is a paper by Vali Sadeh, if you guys know him, and has like about 12,000, I think, citation, and it is using circle packing theory in wireless sensor deployment settings. So they are all useful, but they're not necessarily relevant to the problem that we are interested in. It's because we don't have infinite space and infinite resources to pack. So in our setting, we have limited number of agents, and then we want to place them strategically. So the problem shifts from what is the densest possible pattern to, given our limited agent, what is the best possible coverage that can be achieved, right? So this is our question. So when we talk about the coverage problem with limited resources, the essence of the solution, as you can imagine, is like divide the space into subregions and then assign the agents in a way that the coverage objective is maximized, right? So when we go to literature and look at like what are the tools for partitioning this space, I think the prime example that's going to come out is the Voronoi diagram. I think everybody's, so I see nodding heads that you're familiar with it. So the idea is that we have some sites in the, like a sensor coverage, let's say, problem is like, these are the locations that you're going to place your agents. And then this algorithm partitions the space in a way that every partition, every point in that partition is the closest to the center of that cell, right? But from the coverage problem, the problem is now, how do you find these locations, these sites for your agents? So for that, we have a little variation of this algorithm, which is the Lloyd's algorithm. You start with some initial like assignment, and then Lloyd algorithm iteratively nudges these particles around, and then eventually the space is partitioned evenly, all right? So this is all good, but then what happens is that if we go to practice, and look at our problem, not every area is equally important. So there are parts that you want to pay more attention than the others. So we need to have a priority function and then divide our assets based on this priority function. So in practice, what happens is that we often have this priority function in a sense that either we have statistical data, or maybe you have this satellite imaging or aerial imaging, or you can deploy sensors to understand the scene. And what you would get is this distribution, spatial distribution, which mathematically is just the 2D spatial probability distribution. So now this basically explains what's the importance of every point, all right? So the problem then shifts to, given this priority function, partition their space. Then we go back to the literature. How do the literature handles this? The literature handles this with weighted Voronoi partitioning. So you can put in the weight, and on top of the weight, you can also bring other tools like power diagrams that we can now also assume some relative size of coverage. So the agents could be heterogeneous, and you take that into account. The Voronoi can handle that, and then you end up with this partitioning, and you can see that it's trying to cover the important areas, right? So Voronoi partitioning and Voronoi solving coverage problems using Voronoi is very popular. Just go to Google, or even go to Google Scholar and just search sensor deployment, or all the papers are almost on use of Voronoi deployment. But then we see some downsides to Voronoi deployment. So we thought about some alternatives, and what I want to tell you guys in the rest of this presentation is these alternatives that we thought about and what motivated us to choose these directions that we are going to propose, right? So to get there, let's first look at the objective in the deployment and then move on to the solution. So if you look at the deployment, I personally divide the objectives into two categories. One is the dispatch deployment, and the other one I categorize it as service matching deployment. And what do I mean by dispatch deployment? For this, imagine you have a taxi company and you want to place these taxis strategically around the environment that you have in a way that you have a fair access. So if there's a call coming from this region, so you have this population map, and then you want to place it. So what you would like probably is to place them somewhere in between. All right. So this is fair access dispatch. So you could reach everybody when you get a call in a fair amount. But then you can also have service matching deployment. In service matching deployment, the objective is to provide the service at the point of deployment or around the point of deployment. So for this, you can think about like a wireless access. So if you want to deploy UAVs to provide hotspots, you want to go to the populated areas, right? Or I try to make connections with transportation problems, and you can think of this mobility on demand solutions that you imagine you have these scooters scattered and then you want to strategically place them back. So you want to go to the hotspots and get the most use out of these mobility on demand tools that you have, right? So now let's focus on this service matching deployment. So our interest for the remainder of this talk is going to be on service matching deployment. And now we're going to see why service matching deployment, Voronoi cannot provide the ideal solution that we may be looking for. And for that, let's look at this example. So imagine we have this priority function. There are 4 modes for important areas in the space, and I am deploying 4 agents. So here, these are the Voronoi partitions based on the relative size also. And then as you can see, more or less, it gets to the hotspots, all right? But then if we have more modes than the agents that is available, now we see a difference in the performance. In a sense that now, because we have 4 modes and 2 agents, and the Voronoi partitioning tries to stay close to everybody in the space, we have a compromise. You go in the middle of 2 hotspots. So here is 3, and then if you go to 2, you can see when it's getting shifted and going away from the hotspots. So now this motivates us to think about like, how can we solve this problem, right? So to solve this problem, in my research, what we do, we look at the deployment problem as a 2-stage problem. Instead of tangling the identifying the point and the assignment and doing it together the way that Voronoi partitioning is doing, we separate this. We first want to identify the important points on the distribution, and then we do the assignments, send the agents to these important points. So when you have this framework, then we have 2 questions to address. One is going to be how to find points of interest, and the other one is going to be how to carry out the assignment in an optimal manner, right? So that's going to be now the focus, and let's get started with the first question. How do we identify these important points? So for this, again, if you go back to the literature, what you will see probably is not something like a clustering, right? If you go to clustering, you see it's quite relevant. Often we have the spatial data, right? And then when you have the spatial data, for example, you can give it to the k-means partitioning and clustering algorithms. And what k-means does is that it groups the data points into k pre-specified number of clusters that you identify, then finds the center of these clusters, and every point is assigned to the center of the cluster that is closest to. So you have immediately a partitioning and sort of a hotspot, right? So you can do this a little bit more informed in a sense that instead of k-means, you can also use like fitting multimodal distribution to your data. And the most popular method is the Gaussian mixture model. Gaussian mixture model is consisted of like a bunch of Gaussians that you add up, and you can fit the data. You again specify the number of the bases you fit, and when you fit the data, what you see is that Now, every basis acts like a cluster. So you have the center of the basis from this process, and you have the space divided. Now also you have the statistical distribution of these points. They're not just the points around the Hudson. Okay? So you can do this, and actually we have used these methods in our earlier research, but then through those research, we identified some downsides to these methods. One is that they are sensitive to initialization. Yeah, there are algorithms that help us to initialize them properly and find the solution. So let's say that's taken care of. But then the other challenge that they come with is that they are parametric, right? So parametric means that you have to give to these algorithms the number of the clusters that you want, and then they go fit. And let's forget about that. Maybe the distribution is not really well fitted with a GMM. Let's say you can do a good job, but this fact that you have to identify and give the number of the clusters in advance, it could be a downside. So to see this, I have this example. So basically what I have done is that I have a GMM with 12 bases. I sampled from these GMM. So these samples are fabricated based on the knowledge that there are actually 12 clusters. Then I asked to fit like 7 bases. Now, what happens is that because I am underfitting, you're gonna see that we'll have 2 things. First of all, we end up with what we wanted to avoid, which is we're only going to these compromise points. And then also some spots are gonna be missed. So now we are looking for a solution that could avoid this. So the solution we offer is going to statistical sampling. So we basically go to statistical sampling literature and say, okay, these important points can be identified by sampling from this distribution. Okay, so sampling the distribution, I don't know if you are familiar or not, but if you Google it again, this prime solution that is gonna like a mainstream solution that's gonna come out is this MCMC or Markov chain Monte Carlo, or you may have Gibbs sampling. And they can give you the sample, but the challenge is that they need a lot of samples, like you need 1,000 something. And then there's a warm-up process and all of that. So they're not quite relevant to our case when we want to fit just limited number of samples. So if you want to work with limited samples, I don't know again, if you heard of this Stein variational gradient descent method. So part of my presentation, I think I want to highlight some of these tools that not necessarily us, I think other people are looking into it, is that they're coming all from machine learning and data processing literature, and you can translate them to the engineering problems that we have. So this is a kind of algorithm that I would highly recommend. And so let me tell you what this is and how it could be useful for you guys. So the idea is that I want to fit samples to this distribution, but I want to work with low number of samples. And the literature has shown that this SVGD algorithm, it does a very, very excellent job with that. All right. So what is SVGD?
May I ask a couple of questions actually to clarify, because I'm thinking from a vehicle-to-vehicle communication context. It looks like here you are considering your own agents. You are going to send them to the field, because in a vehicle-to-vehicle communication situation, we could sometimes recruit the equipped vehicle to serve, to relay information, or serve kind of a similar role. So that is not the case. You're not considering.
So right now I'm on the placement, but then down the line you may want to say, okay, these divisions and all of it, I want to also do it in a distributed way. So I'm talking about agents. Usually when we talk about agents,
you are going to send them. You have total control.
Yeah, so this is sort of an assignment problem.
Okay.
Right? But then you can also, like coverage control, you can have a dynamics. We're gonna see there's a dynamics that pushes these particles. And that part of it now you can relate it and say, okay, maybe this is coverage control that not only partition and assignment, move towards that too.
Exactly. Right. So that's what, okay. So thanks for the clarification. And then another kind of set of questions. It definitely looks like it's wireless communication, or actually you were talking about scooter redeployment. It might not be communication. But my question is, there kind of a coverage zone? It looks like it's assumed here? For each agent, you have a.
Yeah, the idea is that like this distribution that you see,
Mhm.
you have some historical data.
Mhm.
Like you can have aerial imaging, and from that you say, okay, there are a lot of people here, and like people here and people here, or
Yeah.
historical data that shows like when and where are more populated at each time. Now the
Okay.
idea is that you have a mobility on demand that is very smart. You don't just randomly scatter them. You just look at this historical distribution data and say, okay, this is the hotspot, this is the hotspot. So that the picture I showed, it was from Baltimore, that actually some guy goes in the morning, picks up these scooters, and then goes and races them. Yeah.
Actually, I might need to apologize again I'm thinking from the transportation point of view. The density or hotspots, actually transportation is demand, right?
Yeah, demand,
So you are
exactly.
sending, the agents or, the scooters are supply. So I'm
Yeah.
thinking from the demand and the supply point of view. So demand is definitely from historical pattern. We have a
Yeah.
demand map. This is a really cool way of thinking. So my question then, is this supply is kind of like a wire, again, I'm considering wireless communication. Definitely, there's kind of certain coverage range.
Mhm.
Beyond that range, and then the communication is not reliable or almost zero. There's kind of like a drop in our formulation. We have a one within the range and then drops to zero. So I'm asking if you have a kind of like a continuous drop in service, or you also have a 0-1. Within the range is one.
These are all good questions, and I think somehow I'm gonna touch on them. So the idea right now here is that I'm gonna identify the hotspots,
Mhm.
but then now we're gonna see in the other part that I'm gonna assume a spatial distribution for your service.
Mhm.
So like, for example, if I am a camera, I'm deploying around myself, the cameras have like areas that they can see very well,
Right.
and then it fades, right?
Yeah.
So now I want to place my cameras in a way that I also consider their quality of service.
Okay.
So
You have all different kinds of
yeah, so this
supplies.
this is just a step by step.
Okay.
I think maybe I will answer your question when we are talking about the assignment part.
Okay.
All right.
Yeah,
So
that's
here,
what I like.
just the question will be finding these hotspots, and how do you do it?
So I understand that you know P of X, and then sample from it. Which to me just seems like conventional Monte Carlo simulation. I'm not sure what the.
Yeah, that is what I'm saying, right? This is a Monte Carlo simulation that you sample from a distribution.
Okay.
But if you do that, just give the MCMC or give sampling and say, I want 5 samples from this distribution. It's not gonna do a good job. It fits, but it needs a lot of samples.
Sure, okay.
And then let me show what the algorithm is.
Yeah.
And we'll come back to your question. I think part of your question also answered like in my next 2 slides. All right. So what is SVGD? This is the simulation of the SVGD. So the idea in SVGD is that like we have this theory in statistics, it's called statistical inference. Like, so in statistics, we work with distributions, and when these distributions are complex, it's actually very hard to sample from these distributions. So the idea in statistical inference is that you try to fit this complicated distribution that you have with a simpler distribution as close as possible, right? So there are different methods for statistical inference, and SVGD or Stein variational inference, before getting to the GD's algorithm, the gradient descent. So SVGD, what it does is that it starts with a simple distribution, and then it finds a deterministic map, and it fits this other distribution. So you would sample from this distribution and sort of map. Through the transformation, you map this, all right? So in the Stein variational inference, this map, it becomes this rule that actually it looks like a gradient ascent. So basically we have these peaks, right? This is a distribution, and we want to go to the important points, to the high areas, right? So it ends up with having a gradient ascent term, which pushes you to climb over and go to important points. But then it's optimization algorithm, and you know that if we start, we might collapse all of us to one point, right? So what it does is that it has a repulsive force, and it pushes the particles out, and it avoids collapsing into just one mode. And what you will see is a behavior like this, that you start with bunch of particles, and iteratively it pushes them in the space, and then they go and fit this, right? So you see a lot of points in the important areas, and the number of points in less important areas, it drops. Okay, and you can see how it works with this. I don't know, I think it's here 20 samples maybe, but give MCMC or give sampling and ask for 20 samples. It's not going to be like this. It's going to just generate points and discard, generate points and discard, and it's not going to give you this kind of fit, right? So, and if you are interested in sampling, I would highly recommend take a look at this. It's a very simple literature. But now, so we did this, and then if you look closely, it needs a distribution. You may ask, you're sampling from distribution, and you need the distribution. And then when you need the distribution, you can think about its parametric. But what happens with the SVGD is that actually this is completely non-parametric, in a sense that there are methods called kernel density estimation, which you have the raw data and it fits a distribution. It's not constrained like the Gaussian mixture models, and they can identify the clusters themselves. So here's an example. Again, I generated a ground truth from a GMM with 5 bases, and then I sample from it. I take these samples and give it, and now say, okay, I didn't know the number of clusters, and I say, okay, do 4. Again, you see the underfitting. But if you give this to KDE, I don't specify, just give the data, and this is the mechanism of the KDE. It will identify, you can see all these areas are naturally identified. And then once you have the KDE, this is a continuous function, and then you can take the gradients and just run this algorithm. And for all of these, there are libraries. You can easily go, there's very simple Python libraries, and you can use them. So far, what I have done is I'm just presenting what exists in the literature. So what is our job beyond being a system engineer and adapting this? We have done some tweaks because they're not specifically designed for the coverage problem and deployment. So here is the tweak that we have done. So if you look, this is just a trivial use of this SVGD algorithm, and I fit these samples. Now, if I put this in the context of coverage, then eventually some agents are going to go there, and these agents have some coverage footprint. Because this is sampling, you can see the particles could be dense, especially if one of the modes is very dominant. It's going to pull most of the samples there. And then you're going to end up with wasteful like overlaps in the coverage. So the tweak that we have done is we consider the effective footprint of the agents, and we go and redesign this repulsive force that the SVGD had to be aware of the effective footprint. And while it tries to fit these particles to your distribution, it will push them as much as like their coverage footprint size. So you can see now they are a little bit spread out while they are still capturing the important modes that you have, okay? So this details, it all comes to designing this repulsive force. I'm gonna skip it. We have a paper, if you're interested, you can look it up. But here I thought like put this just for a little laugh. Somehow, and when these little things or a robot moves, everybody's now wake up. And so this is just applying our algorithm. And I don't know if you guys are aware, this is Dean Magristat's robotorium. And you have any algorithm that involves some form of robots moving, you can actually go there, give it to them, and they will simulate your algorithm. So we have submitted our procedure, and they simulated us, like gave this for us. But again, you can see that they go, but I want to also highlight, even though you can see robots go to those points, still our job is not done. We are not done with the assignment. Now, going forward, after
May I ask a little bit on the simulation? This robot's not autonomous, right?
no,
They are driven by the back end algorithm,
yeah, right now this is like
like autonomous searching.
this is actually, you can think of like, how
Okay.
SVGD works. They start a particle. So you have the motion rule, which is, this is how every xk plus 1 is updated. So they are moving, right? And then the coupling is that there's this repulsive force. So the coupling, it needs to know its distance from every other particle and designs a kernel to push it. So you can think about this as an autonomous operation. So you need maybe some form of consensus-based procedure to allow them to construct this repulsive force. So if you do that, you also have a distributed coverage.
Thanks.
But we haven't explored that dimension. I think it can be done easily. Okay. I think I'm talking too fast, so let me a little bit slow down. So many slides. So now the thing is that, okay, we have this fit and let's say we are happy with it. Now we're gonna go back to comparing it with the Voronoi. We just wanna see how we are doing head to head with the Voronoi algorithm for this dispatch deployment. So here is the distribution that we had, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's say I am deploying 10 agents. And the idea is this service matching deployment. So I want to go to the hotspots. So this is how we do. This is how Voronoi is doing. I think more or less like Voronoi also doing a good job, but you can see some, this is sort of wasted deployment. But more or less, they capture both. But then the challenge that we highlighted, we said that when you have more modes than the agents that you have, now you can see we go to the modes, but then Voronoi goes to this compromising point. So this SVGD algorithm, I think it's a good potential solution for this setting to identify the points of interest. Okay. Now, just to recap, the idea was identify points of interest, and then we're going to do the assignment. So now we are going to focus on the assignment. Voronoi does deployment and assignment at the same time. But for us, we do it 2 steps. So how do we do assignment? So for assignment, we want to also look into, it's not just putting location. We want to look at the reality of what the agent is doing. So agents often are heterogeneous in a sense that they have different coverage footprint. All right. So in the Voronoi setting, the way they handle this is like, they use this power diagram. So if you have circles of different size, there's a mechanism to put it there, and then they can adjust to the size of the circles that you have. But what happens in reality is that the actual sensors or the service that you have, it's not always a circle. It could be anisotropic, meaning that it could be directional, all right? So again, Voronoi partitioning, they looked at adjusting the Voronoi to account, for example, for elliptical shapes or wedge shapes, all right? So this is like going from here to here for the elliptical shape. But what happens is that, again, limited shape, and you have to define the angle, all right? So there's still restriction in this domain. So we looked at alternative ways. And in looking into alternative ways, we wanted to be aware of the actual reality of the sensors. So many sensors, they have very sophisticated footprints, right? It's not as simple as an ellipse or circle or just a wedge shape, a triangle. There's also this thing that the quality of service that you have, what you do in that footprint is not uniform. So for example, if you have an acoustic sensor, you may hear very well in the front, but as you go further away, your functionality degrades. And then the same thing with camera. Cameras, interestingly, they look at this trapezoid. You can see variable in the middle and then it degrades. Okay, so now we have this sophisticated sensor quality. I'm calling it quality of service, but it could cover so many things. It could be like, for example, in this setting, really coming from the sensor's ability, closer to me, I do very well. Going out, I don't do very well. But you can also think about like a taxi that you have priority. I want to, prioritize. I will take more calls from nearby and then maybe few from far away. So that gives you, even though it's a dynamic, you can just consider a distribution for the service that this taxi is going to provide. Okay. Now, what we do in my research, given these realities, is that we define the deployment in a different way. We assume that every agent has a spatial distribution. So there's a statistical distribution that tells what you would do when you deploy. It has you can think about it's a rigid body. It has a shape, but you can move it around and also you can rotate it. So it's gonna hold its shape, but then as you rotate, it's gonna change, all right? And then you can also move it around. Now, collectively, you put them together and they have a distribution, and we have a priority function that gives the events distribution. Now the problem becomes statistical matching. I want this distribution to be as close as possible. And how do I make it as close as possible? I will move the agents and I will rotate. So those are my decision variables. And we measure how close they are in statistical sense. There are some callback-Liebler. So this is just how you compare two distributions, right? Callback-Liebler is an integral and all. So this optimization problem, it gives the framework, but it's very difficult to solve. It's a nonlinear optimization, continuous, and you're deciding position and orientation. So how to solve it? Then we go back to our just two-step procedure that we had. I'm going to identify my points. All right. So this is not still my solution. I want to go find where my agent should go. And here, unlike real estate, it's not about location, location, location. It's going to be location, location, and orientation, orientation. Because that's also the reality that you have. So, but the framework that we are going to adapt is going to be, okay, I can also have more hotspots than the agents that I have. So it's not just one-in-one matching. So what I'm going to do, I want to do matching. So I don't know if you guys have seen bipartite matching. But bipartite matching is that I'm going to take this agent and I want to locally compare. If I go to here, what is my matching factor, local matching factor? So I'm going to compute these costs and I can put it here. And then I have bipartite matching. It's a standard combinatorial optimization problem. And there are methods like Hungarian algorithm, mixed integer programming. They can even solve it in a distributed way. They're off-the-shelf solutions that solves this. So with knowing the priority function, agents can decide who goes where in a distributed manner. But then now the question will come, is priority should take into account both like matching the distributions and also the orientation. I'm going to resolve also move, because if I go here, I can deploy around this point. I have some freedom for that, and I can also change, okay? So the question is, how do we do this? So what we are exploring is computing these local similarities, considering the orientation. So in one of our earlier works, what we have done is we have used a Gaussian mixture model to get the clusters. So when you do that, now every cluster you get is a Gaussian distribution, all right? And then we also considered where the special case that our distribution is a Gaussian distribution. Now we asked, I'll bring my agent here. What is the best position to put this agent and what is the best orientation to put this agent to compute the similarity? So if you have two Gaussians, now what we are doing, I have a Gaussian service and Gaussian basis. There's a closed form solution to compute the callback-Liebler divergence between two Gaussian distributions. So I can do that, but it doesn't account for my freedom for rotation. So in this paper, what we have done is that we have, as you can imagine, you can see that the best matching is going to be when they are parallel to each other. So if you have, for example, off these points, like the means are off and you're not quite parallel, this is the similarity factor you get. But if you move them centers on top of each other and make them parallel, the similarity measure goes down. We want them to be as close as possible. 0 means they're identical or identical in a statistical sense. Any positive numbers, it just shows that the similarity. So this is intuitive, but we also mathematically, if you like math, we have a theorem here that shows that you have to make them center aligned and also just parallel to each other. So now this solves my problem, because what I'm going to do, I'm going to take each one of these to this. I'm going to make them axis aligned. It gives me immediately the orientation and the how I'm going to deploy, and I can use the existing formula to compute the similarity. I have my space Cij, put it there, and then I can do the deployment. And here is the results. This is for the case that I have 12 bases. This is regardless. It's just like give me any GMM, I would just do the best fitting in terms of the deployment. And here is the results. So the blue heat maps that you see is the quality of service of my agents that I have. I have 12 agents. So as you can see, if this is denser, I have sent a stronger agent there. You can see like how faded it is, like this is a weaker agent going there, and the orientations are all nicely aligned, right? So this is one solution, but then, we are relying on GMM, and, we go back to we point out some challenges, right? That this might also end up not identifying the right hotspots, and maybe we want to identify our hotspots with a more informed technique like SVGB. So what do we do with that? So this is the next question we address, that let's say the hotspots come from something else and the clustering is not GMM based, all right? So if these are hotspots coming from something else, you can think about around each one based on the effective footprint of the agents. I can carve out some agents from the shape. And let's say I have a very sophisticated service model. It's a distribution, and it could be anything. I'm going to do samples from that distribution. And now what I'm going to do, I'm going to do sample matching. So I have 2 samples, right? These are the samples of my, let's say, quality of service representing how it is distributed. And these are the clusters in the environment. So I'm going to do sample matching, right? So have you guys ever done sample matching or?
No, I don't think so.
So it's just a
Maybe
way
we found
of,
something but just didn't realize.
yeah. So
Yeah, that is possible.
yeah, this is all like what I'm doing. Like right now, what I'm presenting is like just picking the tools from the literature. I'm gonna tell you when we comment, right? So I'm matching samples. So imagine these red samples are my quality of service, and these blue samples are the samples from my distribution, right? So to compare how close, how similar these 2 samples are to one another, we are going to use optimal mass transport method. So optimal mass transport method, basically, it looks at best matching and it computes the distances and then adds it up. And then after matching them in a way that these distances are minimized, then that number becomes how similar these 2 points are to each
I
other.
think we've done this in like a vehicle re-identification. Like we have one frame of a bunch of vehicles and then another frame of vehicles, and we want to match which vehicle are which vehicle. I think it's
Yeah, this is like
some
an
idea, right?
assignment.
To match the 2 vehicles. So
Yeah. So
okay, it's called sample matching.
yeah, so this is like optimal mass transport, that you
Yeah,
just
right.
consider the what is the cost of transporting this point to that point. And there's also related like to earth mover problem. If you look at like,
I want to match 2 vehicles of the same vehicle and
Yeah, yeah.
using all kinds of characteristics. Maybe that is a distance.
right now,
Different distance.
you can use different measures, but if you use like a Euclidean distance, between them, this is like a optimal mass transfer, okay? So, but now what happens is that the regular optimal transport is not gonna work for me. I can put them here and put them there and compare them, but I have the mobility, right? I can move my samples and I can rotate samples. So again, think about samples are rigid in a sense that their relative distance to one another doesn't change, but I can get them and move them, right? So it will affect the similarity. Then how do you decide, like when I'm deciding the similarity, what rotation and what position I have to eventually just consider? And that's going to give me the rotation and the position for deployment. So for that, so here's what I'm saying, right? So here it is. If you move the points, now you're here. The similarity is just now the matching is even different. And then the distances, you add them up. And that becomes the similarity. This is way more similar than this one, right?
So why are you calling it optimal mass transport and not just bipartite matching? Is there?
It is the same thing.
Because there's no weights, right, associated with the points.
You can expand this, right? It's just like yeah, I think we didn't call. You can just do it as a assignment problem,
Yeah.
right? But then it's fancier to say optimal mass transfer. Then you can do earth mover, like it doesn't apply to us, like you can even cut the partition the particles and move and things. So the area is much wider than just matching. But at this form, it's exactly bipartite matching with a Euclidean distance for similarity measure. Now, so the problem becomes how to accommodate this rotation, or just eventually find what's the best rotation, but best location to achieve the best similarity. So for this, the problem itself is, as you said, it's a bipartite matching. Now we introduce the rotation and the translation. So before it was, if you relax it and remove the integer constraint, this becomes quadratic programming. Then what happens is that now you have the rotation matrix. It makes it nonlinear, much harder than quadratic programming and much harder to solve. But luckily, we found the two from image registration. It is called iterative closest point method. So it offers a framework to solve this problem in a sense that you would take these particles, it matches them, then it rotates them. So it just does sequentially, but there's a plan. You cannot just take any optimization problem and do it sequentially, but there's a framework that this will like converge. So we just adapt this thing. And as you can see, I have this and this. Initially, there's going to be very high score, but then I rotate it, bring it here, then I rotate it, and eventually I end up with that, right? That's the best position to place that red spot, and then with this matching, okay? So this is a method that we adapt. And before moving on, I thought this video is cool. So this is just, there's a guy, I think it's hard to see, I can't pronounce it, Gabriel Pierre. He's a French guy. I'm assuming French guy. I haven't looked up where he is, but I follow him on Twitter, and I think almost every day or every other day, he puts some sampling method, visualization. So he has many cool stuff. If you're on Twitter or X, just look him up. So anyway, that's what exactly happening in the image registration, but now we're using it for our problem. So with this at hand, our work is theory development. We are not necessarily an actual deployment. So here is just like some, for example, let's say this is my acoustic signal. And these blue ones that you see, they are the agent, and the background ones are the distribution. And you can see visually how nicely it orients these sensors. Like it had the option to look this way or that way, or what location you can see. This is, let's say, the acoustic. This is the camera. So they do pretty much like a good job. So again, if you're interested, we have a paper on it. You can look it up. So basically right now, if I want to recap, we did all of this work. And we have this two-step procedure. We have local comparison and all of that. We tried to minimize the overlap and all of that. But again, we just sequentially ask questions like, and what we notice is that even though we try to push these apart, our constraint is imposed softly. It's just like a repelling factor. At the end, we end up with overlaps. So now how can I do assignment to be aware of the overlaps? If you look at the bipartite matching, it takes one agent and then it puts it there. It's not aware that previously there was somebody else that maybe covered that area or part of that area. All right, they're not going to assign two agents to one location, so it avoids exact overlap. But then if you have this footprint and you partially overlap, it's not aware of that. So you can be both assigned to these points. All right. So our next quest was how to avoid overlap. Now I want a little bit of a couple decision making, not like bipartite matching. And for that, we have a new chapter. I have to ask if I have time or not.
We have time, and we could save time for questions, but how much time do you need?
5 to 10 minutes.
That's
Is it
fine.
okay? So I will stop after 5 to 10 minutes, but this is the part that I'm very interested in. This is submodular maximization theory. I don't know if you guys ever heard of submodularity.
Yes.
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 So we work extensively in it. I'm going to just give you a very high level overview, but this is an area that I would like to, hear about. If you guys have assignment problems and all, we'll be, nearby to discuss it and do some nice works for you guys. But the whole idea is now we want to resolve the overlap. So this is an example. Let's say I am deploying some cameras, and as you can see, when there is no overlap, my measure of quality of service is the area that I covered. So these are individually and you add them up. But then if you have overlap, and if you look at the joint area covered by this, if returns that, that's going to be less than each one individually, right? So because of this overlap. So we want to penalize and have a mechanism that pushes you out and is aware of this overlap. So now what happens is this brings us to this submodular functions. This is a special class of combinatorial optimization problems that we have a set and we pick an element from this set. Let's say in my coverage problem, I go 0.3, I put it in my function and it returns what's the coverage value. Now I say, okay, I pick 0.3 and 1, and I put it in my function, it considers overlap, and then it gives you a value and so on, right? So you put combinatorial elements in this function and then it can account for this. So overlap results in loss of utility, right? But then submodular functions are a particular class of functions that we know overlap results in loss of utility, but even if we add the value of the overlapping section, this is still going to be less than the value of the functions together. So if your function has this property, you are submodular. So it's a little bit hard to understand in this setting intuitively. Equivalently, you can manipulate this and you can see that submodularity actually turns into this condition. And what this condition is that if you have two sets, like this one is a subset of this, right? Now, if I pick a new element and add it to S1 and pick a new element and add it to S2, and look at the marginal gain. Marginal gain is if S1 plus P minus F of S1 and if S2 plus P minus F of S2. And as you can see visually, when the set is smaller, we have a higher marginal value than when the set is larger. So if you have a problem, which coverage problems usually fall in this category, and is satisfied, this is called diminishing return. As the set grows, this will, the value drops. So these are submodular functions. What they have is that basically when you try to maximize them inherently, what's going to happen is that they're going to push you from going to overcrowded areas, okay? Because you're maximizing this function. So submodular maximization, it comes into like different flavors, but the two that is very relevant to coverage problems are submodular maximization subject to uniform matroid. And our coverage setting is that we have this coverage problem. I have these points to choose from. I have to choose 3 points to deploy this in a way that my utility is maximized. Okay. Then there is submodular maximization subject to partition matroid. In this case, the problem could be a little bit sophisticated. So for example, you can have a coverage problem that you have divided the space. So there are different agents. Each agent has authority over some subregion. This agent wants to deploy 3 in this area. This agent wants to do 2 in this area, 1 and 1 in this area. And now you want to jointly maximize this coverage while, in each area you pick certain numbers. All right, so this is partition mapping. So these are standard forms of submodularity, and there are solutions for them. But then what happens is that submodularity by itself, it doesn't mean anything. It's a combinatorial optimization problem, and it's NP hard. So there's no gradient, nothing. So you have to consider all the combinations to find the maximum value. But what happens is that if a combinatorial function is submodular, there are some nice results that give us suboptimal polynomial time very fast algorithms that you can also quantify this optimality gap. They will give you how far you are from the optimal solution. So your solution is not heuristic. How far from the optimal solution in the worst case. Okay, so the celebrated solution for this, which is like maybe the nice takeaway, it's going to be the sequential greedy algorithm. Interestingly, very simple. What it does is that it says, look at all, like let's say you have 10 items to choose. It goes and evaluates every 10 item, picks the best one, fixes that one, and says, given this point already deployed, now put all the others and then get the best one and you do this one, right? So it's a sequential greedy, and at the end you choose. And now you're avoiding the combinatorial evaluation. It's going to be, I think it's first time you do n evaluation, second time you do another n evaluation. I think it's n squared or something. I don't quite remember its complexity. So very, very easy solutions exist, all right? So now what is the challenge? The challenge is going to be that this is a very popular method in computer science. There are many problems, very fancy names that they fall in this category and they solve it. In engineering, we are using it for sensor deployment and measurement scheduling and many other things. But the whole challenge is that how to show your function is submodular, right? So for that, I had another paper that I wanted to explain, but I guess it all depends on the time. I could stop here or you want.
I just want to say, first of all, I think we know Nemhauser, by the way. He's a transportation guy.
All right, and I can.
Now the greedy sequential algorithm.
Oh, the sequential
Yeah.
greedy algorithm, all right. Yeah, it's being used, but now the difference is that if you are in the context of that, it's not just a heuristic and nice greedy algorithm. It comes with some optimality.
Why don't we take questions and then
Yeah,
we'll
sure.
see how much where we're at that point.
Okay, yeah. Yeah, this one, the only thing that you might find it interesting is that it's for dynamic monitoring and thinking about how a dynamic monitoring can turn into set function that you're picking elements. All right, so but let's just stop here and yeah.
Thank you very much for the very interesting presentation. So I was thinking in cases where agents can move from their positions after the initial deployments, like maybe aerial imaging or in our case, on-demand mobilities. So I mean, I'm not sure if I missed out. Do you think you can decide on optimal number of agents which can minimize the overlaps, still cover the areas of interest?
You're asking about what is the optimal number?
Optimal number of agents to serve your purpose, that is cover the area, and it will minimize the overlaps as well.
So let me see. So you are looking for. So it just remind. I think we haven't thought about it that way. Like we always assume we want to pick certain elements, but the first thing that rings is like a form of circle packing, right? The first paper that I showed actually considers an area, and for them overlaps are detrimental. Like if you have wireless communication overlaps, they can interfere. So for them, it's just they want to avoid overlap as
Okay.
for each, just as much as possible. So the packing problem, it looks into how to densely populate, but it's still, I guess it's not exactly what you're asking, is that how many?
Yes, I
Alright.
mean, you start with the number of agents and you are fixed with that, right? I mean, you are not considering if we can use less number of agents to do the same thing.
I think I can think of a solution, but right now it doesn't come off top of my head as in like, oh, we have done this. But what you're saying is that you want to optimize this kappa I, right?
Yeah.
That how many agents I need,
Yes.
but then you're fixing the cost, or I mean, like in what sense you're asking?
I mean, if I,
Yeah.
I think, yeah, maybe that's exactly what it is, right? So you have heterogeneous agent types, they each have a cost associated with them. You might want to minimize your overall cost, subject to some benefit associated with.
There is like a variations of this algorithm, which is like a knapsack problems that you can put budget, that basically you can say, I want to pack it with certain number, and then you put a budget on the number of the agents that you can. So you can reformulate. Still, if the function that you have, the utility function is submodular, there are like algorithms with optimality gap, like we have it for something else, I don't remember exactly. So what it does is that in this marginal gain that you are computing, it divides also with the cost of that use of that element. So this algorithm also has the convergence guarantees. Not convergence guarantee, in this case, you just pick, you're gonna pick something, but it measures how good that something is.
Thank you. I kind of had another question. So
Let's do,
Oh, sorry.
Please go ahead.
I actually have a follow-up for this. Thank you again. I really like the structure, it's very clear. I assume this like POI identification and assignment one time, right? It's deterministic. So I'm wondering if it works for if, for example, the POI change over time, the density patterns change. And also probably their assignment will also change. For example, you either decrease number of agent or agents need to move like from certain point to other point. Does the algorithm still like work in that case?
So in this setting, usually you can think about maybe the scale, it's just a time scale that is it like you can redo the whole thing, but now maybe when you're doing the matching and you have to tweak it, you add other like constraints to like not do randomly, now you go from here to there. So, and then what we are expecting is that it's not a huge change in your priority function. They're gonna be just moving around. So especially this thing, the SVGD, what happens is that I think it's the right tool in a sense that. So if I go back, let's see. So what it does is that it starts with some particles and it moves them, right? Now, if it slightly changes the priority function, almost the same particles are gonna be nudged and moved. They're not gonna jump from here to there, right? In terms of identifying the points of interest. Yeah, so if it is gradual, I think you can even do it as something that sits there, it converges.
Yeah.
And then once the priority function changes, then the particles themselves.
Real quick, do you have any like rules of thumb for how to set the number of particles for this problem?
So for here, like the starting point could be, because it works very well with a very low number of particles. You can just, for example, start by saying, all right, I'll just put it in the same number of the agents that I have. But then I guess I would put a little bit more and then allow this sequential greedy way to choose. So I'm gonna still be able to pick the most, just most effective points, but then I will explore a little bit more the area.
Yeah, I'm sorry.
I kind of had the same question that he asked, that when the points of interest move like temporarily, so you explained that you have identified these areas with historical data, right? My point is that if it moves like within a day.
So if it moves, like there's two things. If the scale of the change is gradual, these things are just gonna be nudged a little bit, right? And they're not gonna be a huge difference. But then, like, I'm not gonna present the whole thing, but let me just see if this other problem that we studied. I'll just show our simulation to see if this captures the setting that you have. And this is not like a hammer that we want to solve every problem. You know, if the nature of the problem changes, maybe other solutions could be useful. But we also looked at this dynamic monitoring. And the idea was that, okay, I have a bunch of sensors that cover the space, but then I have like some blind spots and I want to use a UAV to just travel between these spaces and visit them. Then what you see around again, we are assuming that there is some authority that or historical data that gives me how the events are happening, right? So the darker the area gets, there's a more probability of an event happening there. Or it could be just idle time. So if there are events and they're sitting, we define a reward that it's just gonna go up. All right. And in this case, the idea is that the agents have to visit and collect rewards. But if two agents go there at the same time, we're going to just collect one reward and we want them to spread out. So this is a dynamic monitoring and very complex problem in the sense that you're not just doing assignment, you're going to design a trajectory and those trajectories should avoid overlap. So the way we fit it in this set function maximization framework and taking advantage of submodularity to push the overlaps apart is that we assume like a moving horizon. Like for example, if this is my C, okay? So what I do is I consider a moving horizon. I carve out a part of the space and I say, okay, what are the possible trajectories for this agent, all right? So I create a bag of trajectory for every agent. And because I carved out a small space, it's rational, right? And then you say, okay, I'm going to pick this trajectory for this guy and I fix it. Now the other agent comes and picks its trajectory, given that that trajectory already visited. And then this is like a way that we resolve this dynamic plan. And then we also take advantage of the framework that we have. Imagine like visiting more informative. This is a kind of a traveling salesman problem. It's an MP hard problem, even solving for one agent. And then if you have multiple and they have to avoid overlap, it's like computationally very expensive. But just thinking a little bit differently outside the box and looking at, okay, I have a pre-assigned trajectories. I'm going to just pick them to avoid overlaps. It helps us basically, here is a greedy, you can see here, if I simulate it, they're just, because they're looking the front, they're not going to move anywhere else. And they're going to be on top of each other because they're not aware of other guys' choices. But for us, you can see how you can spread out and cover more bases.
Did you do it locally first?
No, what we do is like, I'm going to do one design and then they move, I'm doing another design. So it's a moving horizon.
Yeah, okay, because like enumerating paths is NP-hard itself, right?
Yeah.
From any 2 points in a network.
Yeah, so this is like, I am saying, okay, when you are in this box, you can move like this, you can move. So I have a bag of trajectories that I construct.
And so I guess my question is, how are you constructing those trajectories?
You can just consider all the feasible trajectories. I'm not optimizing in any sense, right? I say you go like this, you go like this, you go like this. I have the travel time between each cell. And then I know what time I'm going to arrive. So this is like a little bit of a deterministicness there yet. And then what would be my reward? Because the reward function itself is changing with time. For example, if I am sitting there idle, it's just going to be more and more reward there. So it's going to attract you there.
I guess my only concern is that the number of paths is infinite, right? The number of trajectories.
If you have a grid, not necessarily infinite, right? But you can just, it depends on how accurately you want to capture, but still you're gonna have choices between the, yeah.
And what you're doing makes plenty of sense. I'm just a little bit worried about how you're getting those paths to start with, or trajectory and so forth, but.
Yeah, it's just like, because we are considering it moving horizon, because if you consider the entire like paths over this is like, for example, in this one, our grid is just four grid. And then we do all the possible trajectories in that four grid. And then it takes one step, then we construct another.
So this is a very use application field. When Uber and Lyft, it's kind of better. So, you know, Waymo is the driverless vehicle company. So they sometimes need to rebalance their vehicles, right? Because people want to go from the suburbs to downtown in the morning, and they need to get the vehicles empty back to the suburbs. So like the kind of way that most companies do it now is they put all of them on the shortest path back to the suburbs. But really, like demands could pop up
Yeah.
in the time when the vehicles are going from the downtown to the suburbs. So you would want to spread the vehicles kind of across the lengths of the networks as they're traversing out, so you're covering pretty well. And this problem's like, well, we called it out like 7 years ago. We couldn't solve it very well. Some people are starting to solve it now, but this seemed like a good way to potentially solve it. Let's go here.
We have come up with this like this. When we have done like two-step procedure, it's just like we are opening the constraints and we are giving ourselves some space. And I like this idea. We tried it in here. I never thought about like dynamic planning as a set. You turn a dynamic trajectory planning into just picking a, static, put your hands in and pick one trajectory out. And it simplifies significantly because in the background, there's a reward. And that reward, we could have like idle time. I think this is based on Poisson, like every point there's a probability of one event happening, and it's a Poisson process. And so this heat map that you're seeing is the Poisson process, that the probability, the more you don't visit, the probability of an event happening in that region goes. So there's a flexibility for that reward function to be any function, and still this will work.
Can we incorporate other distance metrics, such as like the travel distance is not always met with the Euclidean distance, right?
Yeah, that's a good question. Yeah.
So if there's a kind of blockage between the two boundaries, so.
And that's actually a paper. I just want to see if I can quickly show. Let me just show you that. This is some work that my student has done recently. So the idea is just like we want to deploy, but then, oops. So we are now looking at like a not flat surface. You can have traversability conditions. So the distances are weighted by traversability factors. So we measure the slope. And so the distance is considered the cost of climbing that slope, right? And then now it's not necessarily like a Euclidean distance. And also in this one, we are considering obstacles exists that you have to negotiate this obstacle. And we measure the distance. This is the shortest distance. There's something called visibility graphs. I don't know if you heard. This is a tool in motion planning that you create a roadmap. It has a very clear instruction of how to do it. And it finds the shortest path in the presence of polygonal obstacles. So for example, he measures his distance in terms of this now. So if you are deploying, I would have liked the examples to be a little bit more exciting, but this is what he delivered. So like this is, let me remember, like, so this is like without obstacles, you go, for example, to these points for deployment. And then if you have obstacles, like, I think this is the one that doesn't consider this. So basically you can see like it goes here to consider the existence of the obstacles. don't remember the details, but the whole thing is that if you compare this, one of them is based on the Euclidean distance and one of them is based on visibility graph. And you can clearly see, like, I think this is based on Euclidean distance. The thing is that I would have put this here rather than here to go grudge. So this is based on the Euclidean distance. You can see it goes here, but this, because considers the visibility distance, it moves to a point that is aware of the obstacle for the distance. So
Would you be able to extend this to say you could have a penalty term for removing obstacle and then maximize the function? Like you get a benefit of having a shorter path or something, but penalty term for removing the obstacle and then to decide if it's relevant to invest in
Yeah,
removing
exactly.
obstacles, something.
So the distances are now weighted with the traversability conditions. Again, I'm not too excited about his graduating, so this is like what he can deliver at this point. I'm not too excited about like the density of the points and all of that, but here it just, the story was that this example should highlight like you consider the traversability conditions of like you might be geographically like Euclidean distance close, but technically you have to maybe travel the other way. So it's aware of the travel time due to the traversability and the obstacle.
So in transportation, this would be like maybe you have some municipality that is illegal to traverse, even though physically possible, you have to go around, right?
Yeah,
Something
I can
like that.
consider all of that. That is like there's like a Pandora box, you open it, there's a lot of tools, like all of these things, just think about in computer science, they are measuring, these are all like exemplar, picking representative examples. So the measures that they use, like comparing images and all of that, it's just like very complicated. But then the theory, as long as the distance is positive, it doesn't need to follow even triangle, like that condition. So some distance measures, because they are not, distance in a rigorous way because of following the triangular condition. But then for this, there's something called exemplar clustering, which as long as the measure that you're using is positive, it's gonna work. And it's not much.
Can I have one question? Yeah. So the coverage length of each agent is based on the physical reach, or like a camera, like their coverage length is based on their physical reach, right?
Yeah.
Yeah. So I wonder like if there's so many like peak demands or focus on small area. In the cases, we cannot avoid the overlapping between the agents coverage rights. So in the case, if we want to maximize the minimizing the coverage, the overlapping coverage, they can like sparse more like agents, even though demand is like concentrated in a small area. So I think the kind of like contradictions happens maybe. So
That's a good question. It comes to what is the utility function? You don't always dislike like overlap. Sometimes like one agent is not enough, and you need to bring in another one. So this is like how the utility is defined. We are looking at like just kind of applications that the utility results in a diminishing return. So submodularity is not like we are going to use it. It's just that the underlying utility first should be from a type that penalizes. You lose value when you have overlap. Then for that class, you use these techniques. So if you want utility like overlap, then we have to analyze and see what kind of utility you have. It's not going to be submodular, definitely.
I actually kind of follow up to that question. That actually suggests some capacity constraint of the of the agents. I mean, for example, for a camera, there might be no problem how many people to track. There still could be if we are going to track people. But I'm thinking about wireless communication. For example, there's a bandwidth constraint. If in the emergency situation, if too many people try to use the same wireless communication, like a router, then that will create congestion problem. In that case, and similar is for like a Uber and Lyft. If we are going to rebalance I'm thinking of batch as a kind of like one agent, they would have a service capacity.
Yeah.
So it may not be good to just send them to the right center of things, maybe in between.
Yeah, we could make them like, maybe there's algorithm, not algorithm, I mean, like this is a problem that one of my students just learning coverage is where we come up for him to just try these ideas. And let's say the idea is that you have like a sensor that could cover this much. So any point that falls in here, right, it's gonna relay your some information to you.
Right.
And then you're gonna use battery for that. And then you have a capacity on your battery. So
Okay,
you can
battery,
take
yeah,
a
that's
certain amount, right? So we can say still maximize the coverage, but be less than
Yeah.
this amount.
That's-
And the interesting part is also that like I can resolve also an issue like
Right.
this, that I can
So
put this.
fewer people.
So first of all, it will look into your budget and choose the populous area based on your budget.
Mhm.
And then it's gonna be also like the overlap, so like maybe it's the sensor relaying like information.
Mhm.
We could even put the cost that if we have overlapping, right? In the range that you have, this you're gonna go to the closest agent,
Mhm.
right? So it will be try to like while you're going to affordable regions, you're gonna be also like aware of the overlap. So if there's a guy already covering there, you better go somewhere else and have a better use of your battery.
Maybe, yeah, maybe that's just like different from what I was thinking. I was thinking, for example, there's a limited communication bandwidth. That, like one cellular tower, I don't know about 5G or whatever, 3G, and they can only serve a certain number of people simultaneously. So, I mean, if we are sending those kind of agents to those very populous area, too many people are trying to dial at the same time. I see there will be problems there.
Yeah, I think I feel like this constraint will resolve it because you are motivated to pick populous area, but now you're bound with the budget that you have for battery of accommodation of the services.
Mhm.
So if you end up, because this constraint is gonna be there in the solution.
You won't
So
send to
you're
the,
not gonna go there, you're gonna go to next possible
that's expensive.
populous that, and for that also, still it falls into like, we don't like overlap and all. I think the
Yes, yeah, no
coverage is gonna
overlapping
be
makes sense.
Sub-modular, but you're gonna have a budget, and then for this, there's also an algorithm to solve the problem. Yeah,
so the point of interest will be different.
yeah,
With
so
this,
that's the thing, right,
constraints.
that you asked about like how many points of interest. So if I have more than my agents, the points of interest, still I'm gonna identify statistically important, but then my agent will have flexibility to go places that is more relevant to its battery.
Okay.
Do you also, can you include in this parameter where you could vary the radius of agents? Like you could have multiple type of agent with
Yeah.
different radii, and then you could.
Yeah, that is like the difference between partition matroid and cardinality, like a uniform matroid. Uniform matroid, you say, I have this, because my agents are homogeneous, I'm gonna just pick 3 points. The functional evaluation is not a function of the heterogeneity. But if you go to partition matroid, you're gonna say, I have this bag of like a different types. From this bag, I wanna pick 2 agents. From
So
this
what if
bag-
it's like, you don't know how many you wanna pick from each one? Like, you could pick in any number, 0 to infinity of each one or something like this. But they each have different coverages, right? And it helps you pick the optimal number of each one.
So I don't have the solution right away, but I'm pretty sure you can formulate it, but it's a little bit different. Like what we discussed is that we have limited resources. How do you account for it? Now you're changing it, as I said, it's sort of a packing problem that I have unlimited.
Well, you have limited resource to buy the agents or something, but you could buy more than one type, because you can imagine like you'd be like, oh, I want to buy 4 of this type, 5 of this type, but I could buy 6 of this type, 1 of this type, something.
So it's like, I think it reminds me of like a production games,
Yeah.
like production games, not the game part of it, but like you can have problems like I want to produce this 2 items and each one has this price, and then like to produce each one, I need this much of each. You can put it together like a linear program. It comes across as in how do you gonna compute the utility? If the utility is linear, like it's just like linearly, like then like this is gonna be linear programming and can be easily like put together. But if the utility is a bit more sophisticated, we have to see. But there are, we can look at it. And that's the part that we say, like, I would like to discuss it because sometimes the problems, they need tweaks and pre-processing to see if this framework is suitable for them.
That seems to be a bi-level optimization problem. That's one way to.
Yeah,
formulate
like in submodularity, there's like a case submodularity that you can have different objectives and all. So there's this whole, as I said, it's a box of tools.
Yeah.
We're very much enjoying playing with it. That you can do like a very creative ways of how to fit things. Like let's say I have 5 items. And I want to assign these items to different producers, and everybody's production utility is submodular. How should I divide this between you guys? So this is not naturally fits in submodular maximization uniform or partition matroid, but what you can do to turn it into a partition matroid is going to say, okay, I have 5 agents and 10 items A, B, C, and D. Okay. So now you can do, okay, I'll create a bag, item A to agent 1, item A to agent 2, item A to agent 3, like let's say. Then another bag, item B to agent 1, item B to agent 2, item B to agent 3. So you create these bags, right? Now this becomes partition matrix. From each bag, you're gonna take 1 element. So then A is assigned to 1, B is assigned to, like if you pick this, you can have multiple items assigned to one agent. So there are like this manipulations that you can reformulate, and there's a lot of fun in this combinatorial optimization.
Do you have training in industrial engineering operations research?
No. No, we just like start with something and then branch out, and yeah, that's why the list of the things that we are working on, it just grows and it becomes like, sometimes it's hard to tell what I'm doing.
Right, let's thank Professor Kia.
Like some transportation papers that I found that they use some modularity. So was just to the point that if you find yourself interested in this, I'll be happy to talk about it.
It was interesting you mentioned like the overlap being a bad thing with the camera sensors. I've oftentimes seen that like if you want to build a resilient sensor network, you would like that.
Yeah.
So it depends on the problem you're solving,
Yeah,
right?
it depends on what you want to do. It's a kind of a coverage problem, but the utility is different.